Hi everybody, welcome to lecture 23 of Electrical Engineering 331. In this lecture we will review the use of phasors to solve differential equations and circuit problems. And at the end we will discuss an example that will connect this material to the material that we did on Fourier series. So the first problem that we'll do today, example 23.1, is the same as problem 5.4 from your textbook. And it says that a system is characterized by this differential equation, and so you're supposed to find y of t. And the values for the various parameters in the differential equation are given there. And as I said, your goal is to find y of t. So let's see how this goes. Now, let me state one thing. Your book gives you a hint to solve this problem using superposition. And what that is referring to is we have two source terms here on the right-hand side of this differential equation. And so what you could do is you could solve for the first source term and get one value of y, maybe call it y1, and then you could solve using the second source term and call that solution y2, and then the overall solution would be y1 plus y2. But there's really no need to do that in this problem. Both of these sinusoids on the right-hand side have the same frequency, and so there's no need to use superposition here. You can solve this problem all in one step. However, we will see in later problems that if the if you have multiple sources that have different frequencies, then you definitely must use superposition and solve for the different sources at different times. So recall that the way that phasors work is that the phasor that corresponds to A1 cosine of omega t plus V1 is A1 e to the j phi1. So whenever you have a sinusoid and you want to find its phasor, just get it into this form right here, and then you can easily get its phasor. And so for instance, the way this would, now notice this first one obviously is already in that form, so the phasor of this is just A1 e to the j phi1, but the way that we would get this second term in that form so that we could find its phasor is to start with the observation that the sine of omega t plus v2 is the same thing as the cosine of omega t plus v2 minus pi over 2. And you can arrive at that result using the cosine of a difference formula. And so since a sine of omega t plus v2 can be written like this, then the corresponding phasor is a2 e to the j, and an angle is phi2 minus pi over 2. And then if you write this e to the j phi sub 2 minus pi over 2, if you write that as e to the j phi 2 times e to the minus j pi over 2, and then remember that e to the minus j pi over 2 is minus j, then you could equivalently write the phasor in this form, which is frequently useful. So now we're ready to look at this equation that we have up here and take the phasors of each side and solve the problem. So if we take the phasor here on the left-hand side, remember that when you take the phasor of the second derivative, you'll get j omega squared, j omega quantity squared, and then we have this C1 and then the phasor of y. Here we're having first derivative, so we just have j omega to the first power, and C2 and y tilde, and then for this term, just C3y tilde. And on the right-hand side here, for these two source terms, we have the two phasors that we have already identified, A1 e to the j phi1 and minus j A2 e to the minus j phi2. And so on the left-hand side, if we factor out the phasor of y, then we get this expression right here. And so we could divide each side of the equation by that to solve for y tilde, which is the phasor of y. And then if we use the parameters given in the book for this problem, this will simplify. It looks a lot nicer. You'll have 10 e to the j power 6. I have switched this phi1 and phi2 are given as 30 degrees. I've switched them to radians because I plan to simplify this final expression using Wolfram alpha. So that's why I've switched it to radians. So in the top then, A1 is 10, A2 is 20. So anyway, this becomes 10 e to the j power 6 minus j20 e to the j power 6. And in the bottom, C3 is 3, omega squared times C1 is 1, and then omega C2 is 3. So it really comes out to this really pretty nice, simple expression for y tilde. But this is sort of a mixed form here. This part is in polar form, but in the denominator we have rectangular form, and in the numerator we have a rectangular form here. And so we want to get all of this as one complex number expressed in polar form, and Wolfram alpha can do that for us. And what it tells us is that number is equal to this, and so that's the phasor of y, and therefore y of t is simply equal to this magnitude times the cosine of omega t for this problem, and omega is 10 to the third radians per second, so 1,000. So cosine of 1,000 t, and then we have in this phase, which is minus 89.74 degrees. And that's how we do a phasor problem of this type. So now let's go to something a little more complicated. In example 23.2, which is the same thing as problem 5.5 from the textbook, this time we have this differential equation. And actually the differential equation is, at least on the left-hand side, is easier than the differential equation that we just did. But what makes this problem a little more difficult is the fact that these two source terms do not have the same frequency. So here it is absolutely critical that you break this problem up into two pieces. You cannot use phasor analysis when you have different frequencies. Phasor analysis is the assumption that is built into phasor analysis is that everything that's varying with time has the same frequency. So that's why we absolutely must use superposition to solve this problem one part at a time. So this is easy to do, though. We'll just say let y equal y1 plus y2, where y1 is what we get over here on the left-hand side when we use this first part of the source, and y2 is what we have on the left-hand side when we use the second part of the source. And notice that I have identified over here in the margin that in the first problem, omega is 1,000 radians per second, as you can see right here. And in the second problem, the value of omega is 2,000 radians per second, as you can see right there. Now this becomes important right away because you know that now when we take the phasor of both sides of either of these equations, well, when you take the phasor of a derivative, you'll get j omega. But omega is different for the two equations, so it's absolutely critical that you are aware of that. So let's see what happens. Okay, in the first problem, here's the 4 times 10 to the minus 3, and j omega times y1 tilde becomes j times 1,000 y1 tilde for the first problem, because omega for the first problem is 1,000. And then we have a plus 3 y1 tilde there, and 5 cosine of 1,000 t just becomes, its phasor is just 5. But for the second problem, when we take the phasor of each side, okay, we'll get 4 times 10 to the minus 3 coming down, but the j omega here is j times 2,000. So that's going to actually change the equation. Now then we get y2 tilde, and then 3y2 tilde, and this minus 10 cosine of 2,000 t will just become minus 10. Okay, so if you solve the first equation for y1 tilde, you will get this formula, which, if you plug that into Wolfram alpha, will give you this. And then if you go back to the time domain, that tells you that y1 of t is cosine of 1,000 t minus 53.13 degrees. And on the other hand, if you solve the second equation for y2 tilde, you will get this, and use Wolfram alpha to simplify that, and you get 1.17 e to the j 110.56 degrees. And so find that in the time domain, and you will get y2 of t equals 1.17 cosine. And remember that for the second problem, or for y2, omega is equal to 2,000, so we have 2,000 t plus this 110.56 degrees. And so then for the overall y of t, we just add these two together. And I believe that this problem, I believe the answer to this problem might be somewhere in the book, and if it is, it might be reported, the second part of the answer might be reported like this, but that is the same as what we have here, because remember that minus the cosine of a minus 180 degrees is the same thing as cosine of a. So this answer and this answer for that second part of y of t, both of those are the same expression. Okay, and so that's how we would use superposition for a problem where the source has multiple frequencies. And so now there's one last problem I would like to do, and this is where we will make a connection between what we've been doing with Fourier series and the rest of our work in this course. And so I'm going to suppose that I have this problem here. I have a voltage source which is cosine squared t, and we'll have an inductor of inductance 1 Henry up here, and a resistor of resistance 1 ohm, and we will define y of t to be the voltage across the resistor. Well, then of course y of t is equal to r times I of t, and when we use Kirchhoff's voltage law going around this loop here, we'll have cosine squared t minus L di minus L di dt minus R I of t is equal to 0. So that tells us that L di dt plus R I of t, just taking those two terms over to the other side of the equation, that's equal to cosine squared t. And since L and R are both equal to 1, that just gives us this differential equation right here, di dt plus I of t is equal to cosine squared t. And again, y is equal to r times I of t, but r is equal to 1, so that just means that y of t is equal to I of t. So as soon as we can solve this differential equation for I, we will have our desired value of y of t, which is what we want, after all, as you can see here. That's what we want in this problem, is to find y of t, the voltage across that resistor. So all we have to do is solve this differential equation for I. But that differential equation is not so easy because we don't have a pure sinusoid on the right-hand side. We have a sinusoid squared. And so that means that initially it looks like maybe we can't use phasor analysis. But let's think about this. And of course, I think you know where we're headed here. What do? We use the Fourier series for cosine squared t, because then we will get cosine squared t represented in terms of sinusoids of different frequencies, and then we can use phasor analysis separately on the different frequencies, put together all of our partial results, and get the final result. So that's exactly what we're going to do here. We have learned already that the Fourier series for cosine squared t is 1/2 plus 1/2 cosine 2t. And so similar to what we did in example 2, we're going to let I equal I1, this should be plus I2 there. So let me stop for just a moment and correct that. Okay, so now we have that plus sign in there. So I is equal to I1 plus I2, where di1 dt plus I1 is 1/2, where this part of the source we will handle as one equation with I1 on the left, and then the part here we handle with I2 on the left. And notice the frequency in the first case is 0, and in the second case it is 2 radians per second. So then when we go to the phasor domain for each of these equations, j omega I1 tilde, since omega is equal to 0 in the first case, j omega I1 tilde becomes just j times 0 times I1 tilde, plus I1 tilde is equal to 1/2. And then j omega I2 tilde, omega is equal to 2, that becomes j times 2 times I2 tilde plus I2 tilde, and that's equal, the phasor here is 1/2 as well. So we immediately get that I1, this first term drops out because of the 0, so we immediately get that I1 tilde is 1/2, which means that I1 of t is 1/2. And on the other hand, if we solve this equation for I2 tilde, we get that I2 tilde is 1/2 divided by 1 plus 2j, and plug that into Wolfram alpha, and that simplifies, you get the polar form 0.2236 e to the minus j 63.4349 degrees, which when you take that back to the time domain, you get I2 of t is equal to 0.2236 cosine of 2t. Remember that for that second term, omega is equal to, for the second equation for I2, omega is equal to 2. So that's why we have to say cosine 2t here, 2t minus 63.4349 degrees. And then y of t is equal to I of t, which is just the sum of these two components. So we get 0.5 plus 0.2236 cosine of 2t minus 63.4349 degrees. Okay, so that's the end of the problem. That's our solution. But just in case you're interested, let's see if we can check this and see if it's correct. And so what we will do, we're claiming here that this value for I of t is the solution to this differential equation right up here. So let's plug it in and see if that's true. So here I have repeated that differential equation, di dt plus I of t is cosine squared of t. And so, and we're claiming that this is the solution. So let's plug it in and see what happens. So what we're saying is we want to know if it satisfies this equation. So we say ddt of that solution plus that solution, is that indeed equal to cosine squared t? Okay, well, when we take the derivative here, of course, the derivative of a constant goes away, and the derivative of 0.2236 cosine of 2t minus 63.4349 degrees, okay, the derivative of cosine is minus sine, and then the 2 comes out. So we have a minus 2 times 0.2236. That's how we get minus 0.4472. And then we have sine instead of cosine, and then the argument. So when we take the derivative of this, this is what we get, and then we bring down the rest of it, and we want to know if that's equal to cosine squared t or not. Now, certainly just looking at this, you really just can't tell. So what I did was I went to Wolfram Alpha, and I typed in, I entered in Wolfram Alpha all of the stuff on the left-hand side, and then I subtracted from that the right-hand side. I subtracted from all of this, I subtracted cosine squared t from it, and then had Wolfram Alpha simplify that. And if you look at Wolfram Alpha, you'll see that it actually plots. When you type in a function like that, it will plot the function. And so it plotted the resulting function. Again, when I subtracted cosine squared t from the left-hand side, it plotted the resulting function, and for all values of t, that resulting function was less than about 0.000015. So in other words, it was extremely close to 0, which means then, so if I can, if taking this away from the left-hand side gives me 0, then that means, of course, that this is equal to this. So, so that's how we would use Fourier analysis, or the Fourier series, in conjunction with phasor analysis in order to really very simply solve an equation like this. And this, I think, really helps to demonstrate the usefulness of the Fourier series approach. Think for a moment about how else you would solve this differential equation. At least using the methods that we have learned so far in this course, it doesn't look like it would be very easy. I mean, you could find the impulse response, and then you could convolve that with this, but that certainly doesn't sound like much fun. So this is a really nice idea. And again, it illustrates the power of the Fourier series. So I think that should prepare you for test 23. And so good luck.